headline figure, if you go online, is if you consider long-term exposures to indoor exposure and long-term exposures to outdoor exposure, it causes, as an estimate, 8 million premature deaths globally per year. What does that mean? It means people aren't living their full lifespans. Their life has been shortened. It means they are dying of the diseases of age. They are more susceptible to non-communicable disease, which means that air pollution isn't just triggering acute deaths. It is, over the long term, contributing to the evolution of the diseases of age. How on earth, though, do you demonstrate that? It's a devilish question. And what I want to talk about today is the potential of picking up signals before disease is evident during midlife to demonstrate that air pollution and respiratory toxins in general are actually accelerating aging profiles. So I'm going to talk about epigenetic clocks. It seemed like a good idea at the time. I'll probably regret it as we go through this talk. I'm not going to talk about this in any great detail because I've got to do this in 15 minutes, but it's just to make the point that we're not just focusing on extending life. We're focusing on extending the period of healthy living, compressing the period where people live with comorbidities towards the end of their life. And to do that, we have to understand the triggers, and many of those triggers, a considerably underestimated proportion, comes from our environment, not just our genetics, although the interplay of the two is clearly important. So this is a question I began to wrestle with, and I'm going to be describing work I did as part of a UKRI project known as DREAM, trying to look at accelerating age trajectories. And the idea was to link this to air pollution, but it took a very long time to get the air pollution linked. And so I started by testing the system I was going to use with cigarette smoking. If you can't show an effect with cigarette smoking, personally, I don't think you're going to show one with much lower levels of air pollution. And we set up a paradigm. This is a figure taken from Ruth Peters' sort of like hallmarks of aging. We all know the hallmarks of aging. Yeah? So we have genomic instability, telomere attrition, epigenetic alteration, stem cell exhaustion, the usual ones. So I go, let's accept that. Let's pick something which ticks all those boxes, which does all that stuff. And I couldn't think of anything which was a much clearer trigger of driving all of those accelerators of the aging profile than cigarette smoking. That's good. And what should prevent it? Well, the opposite would be a diet rich in antioxidants, picking up the earlier theme that oxidation and redox imbalance is important in progressing these things. So I decided that I would use these as a test bed to test the effectiveness of epigenetic clocks. And the reason I wanted to do this is everybody in the media talks about epigenetic clocks as though they are one thing. But there is a proliferation of epigenetic clocks, and they all do slightly different things. And they are all trained in slightly different ways. And I've illustrated that here. They're kind of generational. And these are just like a selection of the epigenetic clocks. We have clocks, this is the first generation of clocks, and they were simply looking at methylation patterns across the genome correlated against age. So they are purely sort of like age-related. And then we have mortality clocks, phenol-age, Grimm-age, Bernabau, and these begin to actually focus on disease traits related to mortality. So we begin to see biomarkers, the standard biomarkers we'd all be familiar with, sort of here in terms of aging. There are mechanistic clocks, so there's a methylation pattern which correlates with telomere attrition, so you can use that instead of measuring telomeres. There's the epitope clock, which actually gives you a measure of cell turnover, a sort of mitotic measure of stem cell use. Pace of aging, again, using a range of physiologic measures to see whether the aging pace is included. And then you have other causality-informed clocks here where we're actually looking at CPG sites linked to lifespan. Now, the reason I like clocks is that when we do this, we use the full sort of like epic array. So what's that? 850,000 CPG sites across the genome. I cannot do a study with enough statistical power using that number of sites. But what I can do is use all of those sites to produce predictive algorithms into a single unitary measure that predicts accelerating aging. So if I'm going to test all of these, I need a study to test them in. And the study we focused on was known as Airwave. Now, Airwave is an occupational cohort led out of Imperial College by Gary Frost and Paul Elliott. It's an occupational cohort of people who work in the police force throughout the United Kingdom. So there are 42,000 of them, but there are about 1,120 individuals for whom we were able to do full methylation across their genome. That's quite chunky for a methylation study. I've not seen one which is adequately powered ever for what they're trying to do. This is at the top end of what is generally done. Now, of that 1,121, we have about 920-ish, 930-ish for whom we have air pollution measures, dietary measures, and cigarette data. So I can begin to turn the handle on this question. Now, the next slide just describes us that here are the details. On average, 41, slightly more males than females, predominantly white. They're police, slightly unhealthy, and overweight, but don't tell the police force that. If you go over here, this is our sort of DAG. This is what we're looking at over here. This is the epigenetic aging, and we've got all these confounders: smoking, physical activity, alcohol use, BMI, diet goes in there, a whole host of household income measures. But we have a few things. So we also have questionnaires on smoking history. Do you smoke? Don't you smoke? When did you quit? Have you quit? How many years since you quitted? And importantly, and I've put this down here, we actually have blood cotinine concentrations so we can compare what people say about smoking with the actual metabolite of smoking, because people who fill in smoking questionnaires lie. So, the data, and I want to get to the data quite quickly because I think it's really important. This is new, and we have, hopefully it will be published. They've got the corrections in at the present moment in time. Look, here we have all our clocks. Chronological age, mortality, mechanistic, pace of aging, causality. And here we have in black former smokers. We have about 220 of those. Current smokers, we have just under 100. And we're looking at the effect, the accelerated aging effect relative to the non-smokers. And we can see these Horvath and Hannon clocks, which everybody uses, simply don't pick up cigarette smoking at all in this cohort, which is alarming. I was quite surprised. Demonstrates not all aging clocks pick this up. But you begin to see it's quite heterogeneous. We do pick up effects of pheno age, grim age. Look, smoking, sort of like current smoking, ex-smoking, Bernabau, we get the effect there again, current versus former, the lead-in pace, current versus former. So we're seeing acceleration of the aging trajectory. All of these have been standardized, which took a very, very long time to achieve. But we can definitely show that some of the clocks are sensitive to smoking. Now, if they're sensitive to smoking, then if you stop smoking, this pattern should reverse. It becomes an internal control, yes? Otherwise, it wouldn't make any sense. So, just before I get to that, this is the cotinine. If you look at the cotinine, you get the same sort of panel. So what you see with the yes-no question, do you smoke, when do you stop, you see, if you use the actual biochemical measurement of blood cotinine, the same clocks come up. It's a validation. If you quit, the clocks which were positive become negative, which is just rather elegant. Yes? So we know that it's kind of working for cigarette smoking. Does it work for diet? Yep. If you have a Mediterranean diet, and it's one of the blessings of the Airwave cohort, they have probably the most detailed dietary information within a cohort of this type ever, so we could do this for the first time. We can see Mediterranean diet is broadly protected with the same sort of clocks that we had before, and that raises a question. Does the Mediterranean diet protect against the accelerated aging you see with smoking? And here's the data. So here we have current smokers and former smokers, and we've divided the population into those who have high adherence to a Mediterranean diet versus low adherence to a Mediterranean diet. And here we have, well, here we have grim age, pheno age, Bernabau again. And what we can see here is this is sort of like we're looking at the high, this is the normal diet, this is the high diet. So there's a significant protective effect of having a Mediterranean diet. And this is the first time this has been shown. We approached Lancet with this because we thought it was an interesting message, and I've just broken the podium, but in the excitement. But Lancet were rather concerned about this message as a public health message because they thought people might interpret this as being, it's okay if you smoke, if you eat enough sort of like fruit and vegetables, which was never our point. Now, the other thing, of course, is we can go into this and we can go really deep into this and we can actually look at what the components of the Mediterranean diet are which are protective. And this is quite nice because suddenly that paradigm we dreamt up 25 years ago suddenly begins to ring true, because here we have the things which are protective: higher intake of whole grains, higher fish intake, higher intake of vegetables, higher fruit intake for both of the clocks where we saw the smoking effect and where we saw the protection effect. So that's interesting, but that's cigarette smoking. For me, that just tells me that it's worth now asking the secondary question about whether exposure to the ambient pollution in the real world has a protective effect. And so that's what we did next. So I've jumped one. So here we have each of these dots are the individuals scattered throughout the United Kingdom that we have methylation data for. And here we have air pollution, nitrogen dioxide, fine particles PM2.5 less than 2.5 microns, PM10 particles in the population. And these are long-term exposure estimates at their residential address. So we can go into the clocks and we focus down onto the clocks which had been sensitive to cigarette smoking. And we begin, I think, for the first time to see evidence that air pollution is accelerating aging in certain clocks. It's a bit borderline for Dunedin pace for NO2, significant with Bernabeu. This is highly significant. For PM2.5, really there's just a borderline significance here with epitoc, but that's an interesting observation because epitoc is really dealing with mitotic cell processes, and so that becomes a bit of a clue for what we do next. And then for PM10, and nobody ever talks about PM10 because they think all the action is in PM2.5, but look, for PM10 you begin to have much more significance, again, picking up these mitotic clocks as well as these other clocks as well. Now, I think this is incredibly important. Because they were mitotic clocks, as we were doing this, a new generation of mitotic clocks were being published because people publish new clocks the whole time. Here are the new clocks which were brought out: stem clock, replitail, hypo clock. They're all actually really looking at cell turnover. And so as a secondary analysis, we repeated the analysis we'd done with these clocks. And we focused on the particles. And if you do, you can see that all of the mitotic clocks are either borderline significant or they are significant. So I think this becomes really quite persuasive that we actually have evidence that thinking about mitotic cellular processes, we have evidence of accelerated aging in these cells. But what about the Mediterranean diet? Because on one hand, as bad as that message would be for cigarette smoking, it would be a pretty positive message for the general population in terms of ambient air pollution, which is not something they particularly have a say in. And we saw exactly the same thing. So here we've got higher fruit intake, higher vegetable intake. Where I've got these in bold, these are showing a significant protective effect of high adherence to a Mediterranean diet with PM2.5 epitoc, stem toc, borderline for hypoclock, and if you go across all of these, we see a protective effect overall. And this is the first time, I think, that we've actually managed to link diet, benefits of a healthy diet, to the detrimental effects of air pollution. It took us a really long time to do this. I apologize for people who've been waiting for this for a very long time, but it was torturous to arrive at this position. And so in conclusion, look, I think we've got some strong messages here, which are absolutely tied into the concept of longevity and what it is to have a healthy lifespan. We have a range of clocks which are sensitive to smoking. Not all the clocks perform in the same way, and there isn't a grown-up discussion presently about what clocks do and how they should be used. They're spoken about in a very sort of blanket fashion, and I think that needs to be refined. NO2, nitrogen dioxide, was accelerated with Bernabeu and Dunedin pace. PM2.5 with all of these mitotic cell clocks, which I think is particularly interesting. Again, different pollutants associated with different patterns of accelerated aging. This evidence that a healthy diet might be protective, okay, is interesting. I think it becomes more interesting when you begin to consider people in the developing world who are exposed to really high levels of air pollution, which are not going to be near safe levels for generations. What can you do for these people? Maybe there's some sort of nutritional modification that can be put in place. And then I think this is important. We played around with this for a very long time. One of the fundamental problems we have in air pollution is developing toxicological models or mechanistic models that explain the long-term cumulative effect of air pollution exposure to link to the long-term cumulative effects which is reported in the epidemiology. It's been difficult historically. I think this epigenetic mechanism allows us to get closer to bridge that. We've done much more. We have looked for actual genes and specific gene signatures for different pollutants, and I think I can safely say different pollutants have different patterns of methylation, and so potentially we might be able to come up with an internal biomarker of lifetime NO2 versus lifetime PM2.5 and PM10, all of which I think will advance the topic considerably. Thank you. I will just end by thanking the various people who were involved, including the Airwave cohort. Thank you.